All right, when you think about famous numbers in math, pi is probably the first one that pops into your head, right? But there's another, more mysterious number that's just as fundamental. Today, we're going to pull back the curtain and unlock the mystery of the number e. So, let me ask you this. Besides good old 3.14, what do you think is the most important number out there? It's a fun question, but it gets us right to the point because there really is another celebrity number that quietly runs everything from your savings account to the growth of populations. And here it is. Meet E. It's approximately 2.71828, and yeah, just like pi, those decimals march on forever without ever repeating. You might look at that and think, okay, just some random number, but it is anything but. This number emerges naturally from one of the most fundamental processes in the universe, growth. To really get a handle on E, let's put it side by side with its famous cousin, pi. They're both irrational constants, that's true. But while pi is the king of circles and waves, E is the master of growth and decay. People call it the natural base, and you're about to see exactly why that name is so perfect. Okay, so a number this important, where the heck did it come from? It wasn't just, invented out of thin air. It was discovered. And its origin story is actually super interesting. It starts not with some abstract math problem, but with a really practical question about money. Okay, deep breath. This is the formal mathy definition of E. And I get it, that lim notation can look a little scary. But trust me, don't get bogged down by the symbols. The actual idea behind this is way simpler than it looks. Let's just break it down with a quick thought experiment. Picture this, you've got a single dollar, just $1, and you find this amazing bank that offers you a crazy good deal, 100% interest over 1 year. Now, if they just give you that interest once, at the very end of the year, you double your money. You end up with $2. Simple, right? But what if they start crunching those interest numbers more often? And this is where the magic happens. Look at this table. If the bank compounds your interest every month, you end up with a little more, about $2.61. If they do it every single day, you're up to about $2.71. So what happens if you keep going, compounding every hour, every minute, every single instant? You might think the number would just explode and go to infinity, right? But it doesn't. It gets closer and closer to a very specific limit, 2.71828 dot. And that limit, that is E. It's the absolute maximum potential for growth when that growth is happening continuously. All right, so we know the origin story of the number itself, but what does E look like when we put it to work? Let's check out its visual identity, the graph of y equals e to the x. So here it is, the classic curve. It's got that beautiful, smooth, upward sweep that just screams exponential growth. And here's a key detail you should always lock in. It always crosses the vertical axis at the point 0, 1. Why? Well, because anything to the power of 0 is just 1. Now, to really get a feel for how steep this thing is, it's helpful to compare it. Since E is roughly 2.718, its graph is going to be just a little bit steeper than the graph for 2 to the x, but a little gentler than the graph for 3 to the x. See? It's nestled right there in that perfect sweet spot, and that's a big part of why we call it the natural base. Okay, enough with the theory. The absolute best way to get comfortable with a number like E is to actually get your hands dirty and use it. So let's walk through a couple of examples and see how it behaves. Let's start with the basics. If you need to figure out, say, E squared, just grab your calculator. You're looking for that e to the x button. Punch it in, and you'll see it's about 7.389. What about e to the power of -1? Well, that's just the same as 1 divided by e, which comes out to about 0.368. See? Not so bad. Okay, but what happens when we start messing with a basic function? Make it a bit more complicated. For example, how in the world would we graph something like y equals 3 times e to the -x plus 1? Let's break it down. The trick here is not to get overwhelmed. You just take it one piece at a time. First, that little negative sign on the exponent, that's a reflection. It flips the whole graph across the y-axis, turning our growth curve into a decay curve. Next, that 3 in the front, that's a vertical stretch. It's going to pull the graph upwards, making it 3 times as steep. And finally, that +1 at the end, that just takes the entire thing and shifts it up one spot. So after you do all that, the flip, the stretch, and the shift, what do you end up with? Well, you get a brand new graph. The y-intercept is now up at 0, 4. And remember how the original graph got really close to the line y equals 0? Since we shifted everything up by 1, that horizontal line it approaches, we call that an asymptote, is now at y equals 1. All right, you're getting the hang of this. Let's finish up with a couple of quick pro tips to help you avoid some common mistakes. And then we'll tackle the big one. Why should you even care about this number in the first place? Okay, here are two huge things to keep in your back pocket. First, and this is a big one, e is not a variable like x, it's a constant. It has a specific value, just like pi does. Second, when you're doing calculations, try not to round too early. Seriously. Keep the e symbol in your work for as long as you can and only punch it into the calculator at the very end. Your answers will be way more accurate.
So, really, after all this graphing and calculating, why the big deal? Why is this one weird, irrational number so incredibly important?
It's because e is, quite literally, the blueprint for any system that grows or decays in a continuous, natural way. It's at the heart of how we calculate compound interest in finance. It's how scientists model population growth. It describes radioactive decay. It even pops up in probability in that famous bell curve. I mean, it is just everywhere. And if you want the coolest part, the thing that makes mathematicians really light up, it's this. In calculus, the function e to the x is its own derivative. And what does that mean? It means it's the only function where its value at any point is exactly the same as its rate of growth at that exact same point. It's this perfect, self-contained engine of growth. And it just makes you wonder, right? What other hidden numbers are out there, shaping our world in ways we haven't even begun to understand?